Cool. Now we should be recording. Okay, so let's begin. Again, if you have any question at any time, just let me know, either by chat or interrupt me. Yeah, so if I forget to stop after 1 hour, please tell me to stop. So I should take a break around 1:15, and then I'll end one recording and we'll continue from there. So today we're taking breaks every hour. So we will split the recording. And I apologize, sometimes I do some typos in my in what I write. So if it confuses you, I saw it mostly. I think I fixed one problem with the complement rule that I did last time, but I saw another typo for another question. But in the video, it works out. But there's still a typo sometimes in what I write. Okay, so back to chapter 5, we flip a coin 3 times independently of each other. Consider the events: A, there is at most one tail, and B, not all flips are identical. So we want to check whether or not these events are independent. So pretty standard question. So you want to check. I believe the exam is closed book. Yeah. Yeah. No comments, but yeah. But yeah, so here the first thing that you want to do is the probability. So we want to compute, or we want to check whether or not this probability, or this equation is verified. That's what we want to check. So you should probably write this, whatever your definition you're going to check for independence, you should probably check. So we want to check if this is true. So we have 3 probabilities to compute. We have to find 3 probabilities. Okay. So what is the probability that there is at most one tails and not all flips are identical? So how would we go about computing that probability? Anyone has an idea? So I'll let you guys maybe 30 seconds to just think about it. So if there's at most one tails, does it necessarily mean that not all flips are identical? And the answer is no. We do have to be a bit careful, right? If there's at most one tail, well, I could have all heads. So the intersection here is not quite. So at most one, yeah. So if it was exactly one head, then yeah, you would be right. Okay, so how do we do this here? There is at most one tail and not all flips are identical. So exactly, so it's what you said, right? So this is the probability of having exactly one tail, right? Exactly one tails. Right? If I have at most one tail, then either I have none or one. But the case where I have none is not allowed, because otherwise I would have only heads. So this intersection actually boils down to the probability of getting exactly one tails. And that is something that we know how to deal with pretty easily, right? Here it's probability of having exactly one tail in 3 flips. What is this? So yeah, pretty much. So here you're going to do 3 choose 1 times 1/2 to the 2 times 1/2. So you don't need to write it like this, but essentially, this is the probability of having exactly 1 success in 3 trials. Essentially, this follows a binomial distribution. So you can use the formula here. The probability of success, tell, is 1/2. So I got 1 success and 2 failures. If you just wrote 3/8, that would be perfectly fine. Three choose 1 is choosing which flip is going to be the tails. If you don't like this approach, think about how many strings of length 3 with exactly 1 tail can you make? Well, the first task that you do is choose a position for your tail. You have 3 options, so you choose 1. And then the rest is heads. So you have 3 sequences with exactly 1 head over how many different sequences of heads and tails. This is the probability of getting the tails. This is the probability of getting 2 heads. Right? So this is a binomial distribution. If you don't want to argue it this way, you can just use a uniform argument. So this is the size of your sample space. How many different sequences of length 3 of heads and tail is there? 2 to the 3, which is 8. How many sequences with exactly 1 head? That's 3. You choose the position of your head and you're done, because the rest is heads. So there's different ways to argue this. If you don't like this, just count. Do a counting exercise. What about the probability of A? So the probability of A, well, we said it earlier. So there is at most 1 tails. We can break it into 2 cases. This is the probability of exactly 0 tails plus the probability of exactly 1 tails. Now this thing we just computed. So what is the probability of having exactly 0 tails? Exactly. So this is just 1/8 plus 3/8, which is just 1/2. All right. Next one. What is the probability of B? Not all flips are identical. So here we want the probability that not all flips are identical. And yeah, that's exactly the idea. So there's several ways to do this one. For those that just joined, just a disclaimer. So if you have any questions at all, not from anywhere, just let me know. I'll prioritize your questions first. So if you have any questions, just let me know. And today I'll be splitting the recordings into hours. So it should be easier to manage and everything. So in about an hour, I'll be stopping the recording. We'll take a break and then we'll proceed from there. Okay, so again, here, that's exactly correct. So here what we will do, there's several ways to answer this. You could list them out, which is not the best way to do this, or you could use the complement rule, right? You could do, this is 1 minus the probability that all flips are identical. And that's pretty easy to deal with. You only have 2 cases out of 8. Right? This is 1 minus 2 over 8, which is 6 over 8. Now, you have your numbers. Now you just check whether or not the equality is verified. So in this case, is the equality verified, yes or no? So is this times this equal to this? And the answer is yes. Right? Now note times 6 over 8. So how did we get A and B? A and B comes down to understanding that this event boils down to this event. Right? So if there's at most one tail and not all flips are identical, so here I have 2 cases, right? Either I have exactly one tail or no tails. If I have no tails, it means that all my flips are heads. So this cannot happen. If I'm in A and B, I cannot have no tails. So this yields only one case. There's exactly one tail, and that's why this is equal to this. And then the probability of exactly one tail in 3 flips is usually pretty easy to deal with. But you choose which flip is your tail, and then the probability of getting a tail. So here I wrote it as a binomial distribution. You don't have to do that, but it kind of comes from there. It comes from a binomial distribution, or you can make a counting argument. It's up to you. There's several ways to argue this part. For A, B are independent. So you tell me 3 choose 1. What does it represent? Exactly. It just, so you have 3 flips. You need exactly one tail. So you still need to choose which one of your flip is the tail. And then the other 2 will be the heads. So 3 choose 1 is choosing the position of one tail. So this is a pretty standard question. And again, if you don't want to argue it this way, you can just make a counting argument. That's also perfectly valid. You can just tell me, well, I have 8 sequences in total. How many of them contain exactly one tail? You can also do it that way. You don't have to do it this way. No, because you have to have the 3 choose 1. The 3 choose 1 is very important. The probability of getting exactly one tail is not 1 over 8, it's 3 over 8. All right. Next. So here I chose a bunch of questions. Well, they look the same. The next 2 questions look the same. And you've kind of done similar question in your assignment. It's just it's worth going over, I think. So 2 players, P1 and P2, takes turn. Yep, they take turn rolling a dice. 2 fair and independent dice, where P1 starts the game. The first player who gets a sum of 7 wins. We want to find the probability that player 1 wins the game. So it looks a lot at like your assignment. It's essentially the same question as your assignment, but now the probability of winning is different, 5.70. Okay, so let's just remind ourselves what we did in the assignment. So in the assignment, we looked at something like this. So first of all, if I say let x be the random variable corresponding to the number, rows. So it's not necessary to answer it like this. I'm just making a point, just a comment. So a comment. But if you know this, and it kind of tells you what kind of probability you should be looking at. So a comment, let x be the random variable corresponding to the number of rolls that player 1 makes. What kind of random variable are we looking at?
Geometric.
Geometric, okay, exactly. Why? Because the player 1 will keep doing something until he succeeds and player 2 fails, right? But essentially, it's a repetition. This experiment that we're doing is repeating the same thing until the first time it succeeds. When you have something like this, you should think of geometric distribution. So now if you remember your formulas for the probability in a geometric distribution, well, you're pretty much done. So essentially, we're going to kind of refine that formula again. So here, if we look at the probability that player 1 wins the game, maybe I should write my comment. What kind of variable is just for those that are going to read this? Okay, so we want the probability that player 1 wins. So I'll just write it like this. So this probability is equal to what? It's equal that he wins on the first roll plus, and now I'll be a bit more precise, on his first roll plus the probability that he wins on his second roll plus the probability that he wins on his third roll, and so on. So we've pretty much done this question in the assignment. We'll just modifying it. Okay, so what is the probability that on his first roll that he wins? So what is the probability that I get a sum of 7? So maybe, yeah, exactly. So here you can just probability that sum is equal to 7 on one roll. What is it equal to? Here there's several ways to argue this. You can just list the outcomes out of 36. I think that's probably the quickest way to do this. Switch my keyboard like this. So here we would be looking at that, the size of 1, 6, and so on, 2, 5. I think you all know this, but I'm just writing it for the sake of writing it. 3, 5, 2, and 6, 1. That's looking at the size of this set over 36. I have 36 different outcomes. So that's 1 over 6. It's writing here. Let's see. Okay, so the probability that he wins on his first roll is the probability that on one roll, on the first roll that he makes, he gets a sum of 7. So this one is 1 over 6. So here I get 1 over 6 plus. Now what do I add after? what is the probability that he wins on his second roll? So what needed to happen now? He fails the first, and what else? And player 2 doesn't roll a 7, right? So they take turns. So it means that he fails his first, player 2 fails, and then he wins on his second. So what does that mean? It means there was 2 failures and 1 success. What about his third toss? Well, if he went to the third toss, it means that both players fell 2 times, right? On one round, they both fell. On second round, they both fell. On the third round, at the beginning of the third round, player 1 succeeds. So here, how many failures does that make? That makes 4 failures followed by a success. So here the idea is, okay, if you write this, if you had this question in your exam and you wrote this, that wouldn't be bad. But the idea is to just, instead of writing this, it's much better to write the following. Player 1 wins on the kth round. What is that probability? So on the kth round, what happened? Well, you say, how many failures was there? If I'm on the kth round, how many times did we fail? Exactly. So not quite, we have to be careful. It's not 2k, it's 2k minus 1, right? So on the first round, it works out. Right? So 2k minus 2, which is the same thing as 2k minus, I'll just write it here. It's 2 times, 2k minus 1. So it's 2 times k minus 1, I should be saying. So 2 times, and I'll write it, k minus 1 failures, right? So k minus 1 represents all the previous rounds. Both players, they each failed k minus 1 time. And then on the first toss of the kth round, we had a success. And how can you argue this in English? So what would be the justification for this? One line that would be sufficient. You would be saying exactly what I just said. You would say, in the previous k minus 1 rounds, both player fails, and the kth round, the player 1 succeeds. And that's it. That's all you need. You don't need to argue it like this or make a pattern argument. You can really just say this, and that's to the point. All right. So now, what do we do? Well, this essentially what we wrote at the beginning. The probability that player 1 wins is equal to the summation of these probabilities, right? So probability that player 1 wins is equal to the sum. Now I have as low as 1 round, so k is equal to 1. And what is the range of my summation here? How far can I go? So how many rounds could this take?
Infinity.
Infinity, exactly. So again, this question, we've dealt with it in the assignment. Just going over again. So sum from k is equal to 1 to infinity of these probabilities, so of this thing. Now you just plug it. I'll write it at the bottom here instead. So this is equal to what? So this summation times this thing. Now, again, the point of making that comment at the beginning is that this essentially boils down to a geometric series. It is a geometric distribution. So what do we want now? So we want this probability. So we can pull out the 1/6. We can rewrite the sum as something slightly different. So here I have a power of 2. So instead of keeping it there, I can put it there. So this will become 25/36 to the k minus 1. And now, oops, sorry, my 1/6 should be in front, like that. And now, how do I modify this? Well, a geometric series starts at zeros. Can I just shift this index to 0? The answer is yes. When k is equal to 1, you have 0. When k is equal to 2, you have 1. So you can just make the shift. So instead of, you can start at 0, and then you can put a k here. It's the same summation. Now this really looks like a geometric series. And you have a formula for these type of series, right? So this is equal to 1/6 times 1 over 1 minus 25/36. That. And now, how does this simplify? So if I do the math, which I'm terrible at, that's 1/11/36, so that's 6/11, right? Yep. 6/11. So again, very, very, very similar to the question that we've seen in the assignment. So if you understand one of these questions, you pretty much understand all of these questions. The only thing that changes is how many players there is. So if I added another player, it would increase the number of failures that I would need, right? So if I have player 1, player 2, player 3, well, this is no longer 2 failures, it would be 3 failures. Here I would have 6 failures, and so on. So if I add players, it just increases that power here. And the other difference that you get is, well, what are they actually doing? Here we were rolling a dice and we wanted a sum of 7. So the probability of success changes. But that's pretty much the only 2 factors that change. The rest is the same. And usually we'd look at player 1. If we looked at player 2, we would have a slight adjustment to make. So if we think about player 2, so note probability that player 2 wins. Is there a quick way to find the probability of player 2 wins after this? So what would be the probability that player 2 wins? Well, here there's several quick ways, right? 1 minus, yes, exactly. So which is equal to 5/11. Is there even another way that we could have gotten this? So that is the one correct way. But what I'm trying to say is that, okay, the probability that player 2 wins is equal to the probability that he wins as a player going first, given that player 1 fails on his first toss. So here, what I'm trying to say is that the probability that player 2 wins is equal to the probability that he wins in a game where he goes first, given that player 1 fails his first toss times the probability that player 1 fails his first toss. So what is the point of doing this? If this works if you have 4 players, 7 players, 10 players. Whereas this 1 minus trick doesn't really work if you have an extra player. Okay, so in the case of 2 players, this works out perfectly. But if I add another player, I cannot do this, right? So the idea here is, okay, another way to get the probability that player 2 wins, just think about, okay, well, the probability that player 2 wins is equal to the probability that he wins in the game where he went first, given that, I should say, given that player 1 fails on his first toss, times the probability that player 1 fails on his first toss. Right? I'm implicitly using total law probability. Right? So here I'm adding a 0. What is the part that I'm missing? Is this event can be split into, with respect to 2 events. Either player 1 fails or succeeds. So it's the probability that he wins the game given that player 1 fails on his first toss, or it's the probability that he wins the game given that player 1 succeeds on his first toss. And this part is 0, right? If player 1 succeeds on his first toss, then player 2 cannot win. So this is total law probability. And the idea is, okay, well, this is 0, right? So this part is 0. So now I'm just left with the probability that player 2 wins in a game where he goes first, given that player 1 failed. But we know what is the probability of the first player to win. Player 2, even though in the initial game he was the second player, now that player 1 failed, it's like he's the first player now. So this part we know from the previous part, and this part we know. That's 5/6. So all I'm trying to say, all this to say is that once you have computed the probability of player 1 winning, the probability of player 2 winning is just 6/11, the probability that he won if he went first, given that he went first. So times the probability that he goes first, which means that player 1 fails. Sorry, it's 5/6. And now this is equal to 5/11. So the trick here is a better trick because if I add another player, I can do the same thing. So I don't rely on complement rule here. So I'm pretty sure that's what Professor Holden did in his solution to assignment 4, something like that. So that's what he did here. So if the complement rule works well because we have 2 players, but in general, if I have more players, you need a bit of work. Yeah, so the idea is the probability that player 2 wins is equal to the probability that he wins given that player 1 fails his first toss times the probability that player 1 fails his first toss, plus the probability that player 2 wins given that player 1 succeeds on his first toss multiplied by the probability that player 1 succeeds on his first toss. So what did I use here? This is total law probability. Now this whole portion is 0. Why? Because this probability is 0. If player 1 succeeds on his first toss, then player 2 cannot win. So this whole thing goes away. So now what is that probability? Well, player 2 wins in a game. Player 2 wins given that player 1 fell on his first toss. So the probability that he wins given that player 1 fails is the same as if he just started the game. Right? If player 2 now finds himself in a starting position, then this probability is the same as 6/11. It's kind of like he just started the game given that the first player fell. So I took the probability that he wins the game as if he started, multiplied by the probability that player 1 fell. And it gives you the probability that player 2 wins. It's another trick to get that probability. And it works better. It's more general than the complement. It works for several players. So in your assignment, in assignment 4, that's what you had. You had 3 players, not 2 players. That's why here. So the probability that player 1 wins, he can win on his first roll. That's 1/6. But he might win on his second roll or third roll. So there might be more than one round to this game. So this game could take a while to finish. So the probability that player 1 wins on the KF round is this thing. And that's the justification. Right? If there is K round of the games, it means that there was K-1s in which both players failed. So that's what the probability is of K-1 failures, for 1 for each player. Then if he won on this KF round, it means that he rolled a 7. So the 1/6 is expressing that. So the probability that player 1 wins the whole game is the sum of these probabilities. You need to account for all different numbers of rounds this game could have taken. And now this becomes a 6/11. It becomes, you turn this into a geometric series. So again, that's exactly, you have the solution to a question like this. So the trick to get 25/36 is just powers exponents properties, right? 5/6 to the 2 times K-1. Well, this is the same as 5 to the 6 times to the 2 to the K-1. So I can just pull out the power of 2 and multiply it. Well, not multiply it, but just distribute it on both sides of the fractions. And there's a 2 here. So again, so if you're not sure about this question, just go check the simple solution for your assignment 4. It's pretty much the exact same thing. Okay, next question. Almost the same identical question. So we'll just have to change a few things. So by flipping a coin repeatedly and independently, we obtain a sequence of heads and tails. We stop flipping the coin as soon as the sequence contains heads or tail heads. Two players, player 1 and player 2, plays a game in which player 1 wins if the last two symbols of this in the sequence are head-head. Otherwise, the last two symbols in the sequence are tail-head, in which case player 2 wins. We want to find the probability that player 1 wins the game. So it looks pretty much the same. Now the probability of winning is different. All right, so I'll let you guys 1 minute to think about how we would tackle the problem. The idea is exactly the same. So the probability of player 1 winning is he wins on the first round, second round, and so on. So now what I have to think about is what is the probability of winning and what is the probability of failing. So again, the idea is how would you justify this, right? So on the exam is not the answer is important, but the justification is much more important. So there's two outcomes here. We look at the ending of the sequence. So we flip the coin a bunch of times and we stop whenever the end was head-head or tails-head. So we flip the coin a bunch of times until one of these two things happen. Player 1 wins if this happened, and otherwise player 2 wins if this happened. So this wording is a bit odd, okay? Exactly. So here the kind of different part is that no one win on the first toss, right? So you could think of this question as they each flip a coin until this happened or this happened, and they take turns flipping the coin. It doesn't matter who flipped the coin. That is the point here in this question. It doesn't matter who flips the coin. They just keep doing something until something happens. One of the two things happened here. So here it is slightly different. Not necessarily. It's one or the other.
They said the probability in which B1 wins, not B2. So that means like B1 has to win fast, according to my
No. So it's again the important part is there's no there's no turns here. There's no I'm flipping a coin and you're flipping a coin. Like it could be someone else that flips the coin and then they look at the outcome. They stop. So you stop flipping whenever this or this happened. If this happened, player 1 wins. If this happened, player 2 wins. And yeah, that is correct. So what Tanesh said is correct. So on the second toss, the probability of winning for either player is 1/4. Yes, order does matter, but you don't know whether on the first toss if you had head or tails. You don't know that. So Oh yeah, I see what, maybe that's what you meant. Maybe I misunderstood. Sorry. So yeah, now I see it in chat. So is that what you meant? Is okay? Yeah, it does. I see what you meant. So yes, if you flip a tail, then it's looking grim for player one, right? So here, the probability that oh yeah, so it is a bit, maybe it's not as hard as I thought it would be. So maybe it's much easier. So here, the probability that player one wins is what? It's the probability of getting head first. Getting head, which is what? Okay. So now we'll split this with respect to the first toss. The probability of getting head, given that the first toss is head, multiplied by the probability that first toss is head, plus the probability of getting head, given that the first toss. So here you don't even need to do it this way, but I'm just making it formal. I think you can just write in English. First toss is tails. Probability that first toss is tails. So again, what did I use here? This has a name. It's called total law probability. So again, I think that's what you meant, right? So here, the whole point is that if this happens, can player one win? No. So now we're still kind of reaching an interesting question, is that it doesn't matter how far are you, like you could go flip a bunch of tails. As soon as you flip one tail, well, if the next thing that you follow it by is a head, then it's over for player two. But I'm trying to see if that's actually the intent of this question. I think so, right? Yeah, I do think so. Yeah, no, that's the intent. So yeah, the intent is this is zero, right? This probability here is zero. If the first toss is a tail, well, player one cannot win. So this probability is zero. So now what is this probability here? So this is, I'll just write it here. This probability is zero. Equal to zero. And you can tell why. Why is this? Because flip tails first. So either, yeah, so I'll just let you guys to tell yourself why. So again, this is zero because if I flip a head tails first, then I need a head at some point. But whenever I get my head, it means that player two wins. Okay. And now what is this probability? Well, this is pretty easy to compute. Probability of getting head, given that I got head first, well, that's a half times a half, right? So the problem, this thing here is just 4. So the probability, again, like all of you said, probability that player one win is a fourth. And I think that's all we wanted, right? probability that player 2 wins is 3/4. So it's not a very fair game. Well, actually, this was not as hard as I thought it would be. So is there any question on this one? Are we okay for this one? So again, the point of making these two questions was just to, that's one thing that we did not do last time, I think, is mention total probability, but sometimes it is useful. So here, the 1/4 comes from these two probabilities, right? This is a half. The probability of getting the first toss is a head, that's a half. The probability of getting head-head, given that my first toss was a half, that's a half. My first toss is a half, so now I only care about the second toss. So that's a half times a half.
But like probability of getting head given that the first is head is just the same as like probability of getting head intersection probability of getting the first head over probability of the first head, right?
Yes.
If we do that, I think we'll be getting a half of a half. Which one?
No. So here, be careful, right? So I agree, and I see what you're trying to say, but if you're not convinced by this, use the definition, right? So you said that this is probability of getting head-head, and first head is first toss. First is head. Now this is over the probability of the first toss is head multiplied by the probability that first toss is head. Right? So this is the definition of conditional probability, but I'm multiplying by this thing. So I'm multiplying by what I'm dividing here. So this cancels out, so I'm only left with this probability. And this probability, like you said, is just the probability of getting head-head. So this is a 4.
Are we not looking at the intersections instead of like
Yeah,
because
no, we are. So this probability here is equal to what?
Half, because these two, the intersection of these two is one head.
No, the intersection of these two is 2 heads.
But the first, so it's saying probability of getting head and the first is head, right? So
Yes.
where they do intersect is like where they have both of them, they have the first flip to be head.
So you're thinking about the sequence. Think about which one implies the other. If I have first is head, do I get head necessarily? The answer is no. But if I have head, do I get the first head? The answer is yes. So which one implies the other? This one implies this one. It means that this event is contained in this one. So the intersection is the contained event.
Oh, I see.
Right? So no, but it is a very easy mistake to make. So it's sometimes you think, okay, what is the actual intersection of my sequence? Where do they have the thing in common? But that's not what you want to think about. You want to think about which one implies the other. If I know that this is true, do I know that this is true? Or if I know that this is true, do I know that this is true? That's what you think about. But it is a very good question and a very good remark. It's easy to make that mistake. So thanks for bringing it.
Any other way to go than this?
You mean
Like, is there another approach that we can walk through than this total law of probability?
you could. So essentially, what this is saying is saying in math what you could be saying in English. That's what it comes down to. You could write this down in English. You could say, well, if the first toss is tails, and the player one cannot win. Right? You could write this and tell me why. And then you say, well, okay, so then the only outcome in which he can win is if he gets heads, if the sequence is heads, the first two position, right? The first two tosses are head, and that's 1/4. You could write this in English. The idea is just total law probability kind of formalize what you wrote down in English. That's the only idea here. So personally, I don't think total law probability is strictly needed. That's one thing where I think you don't really need to emphasize that you're using total law probability, but that's the idea of this question, right? In your head, what you did is total law probability. So that's just the formalization of what you did in your head. Or if you want an English argument, you can absolutely do that. For this question, I think you can. All right, are we good for this one? Yes, okay. So before we continue, like I said, we'll be taking breaks every hour. So I'll make this the first break and I'll just, and the reason for the breaks is mostly so I don't end up with a huge recording again. So I'll stop the recording and we'll resume at around 1:12. Yeah. So let me just stop the recording now.